Hello, this is Maureen Julian. We have completed a study of the 10 2D point groups in Chapter 3. Now we will organize an overview of these point groups. We have 4 crystal systems. We have hexagonal, square, rectangular, and oblique. Hexagonal contains 3, 3m, 6, and 6mm, that is 3 folds and 6 folds, and the rotation axes are going to be 120 degrees and 60 degrees. The square crystal system has point groups 4 and 4mm, and that will have a 4-fold rotation axes in both of those point groups. And then the rectangular crystal system is 2mm, and M will have and finally the oblique group, in which the axes are oblique, that is 1 and 2. The axes are gamma degrees apart, and gamma is not definite. It can be a lot of different choices. You have a great deal of choices for gamma. We want to color our material, and for this I'm going to ask you to buy some crayons or magic markers or whatever you want to do to create color. This will clarify what we're doing and show me in colors that you understand what's going on. We have these are the 2D symmetry elements. We have the rotations. The rotations are 1, 2, 3, 4, and 6, which we've proved, and the plane is just the mirror plane. The rotations are all proper rotations. All of their matrices have determinant +1. For the mirror, it has a determinant -1. And notice, we'll remind ourselves that the symmetry operations for the mirror are 1 and M, which are red for the identity, which has a plus determinant, and the mirror, which has a -1 determinant, and together we color them purple. See Chapter 8 on page 166 for more information about the use of color. We'll be doing this throughout the semester. Just a formal symmetry element is composed of a geometric object, which would be a point, a line, or a plane, and the group of operations related to this geometric operation. In 2 dimensions, we have either points for rotation axes or lines for mirrors. In the graphical symbols, it shows both where the geometric object is and the related group of operations. We have red for the proper operations and blue for the improper operations. We've already gone through these projections, but now we're unifying it, and you can see in the oblique system the point groups 1 and 2 have oblique axes. We remind ourselves that the y is in the horizon, along the y-axis is the B, and along the x-axis is pointing downward. And we have this point and stereographic projections previously discussed, the symmetry matrix generators, and now we have the equivalent general crystal faces. Let's look at that in the next slide. For example, we have equivalent planes in point group 2. So if we just choose a plane, say the 1, 1 plane, this intersects x at 1, y at 1. The reciprocal of 1 is 1, so we get the 1, 1 plane here. If we choose to operate a 2-fold on that, we have the 2-fold will create another plane right along here, and that has an intersection of -1 along y, -1 along x, and that gives us the reciprocals give you the -1, -1. So you can see that you go from hk to h bar k bar, which is what these symbols represent. Then we can put our rectangular crystal system. We notice that these are both perpendicular, and we have these two purples look a bit different, but they're meant to be the same. We have the mirror, and then when we put the twofold, we have and the mirror together, we generate a second mirror, and we have notice that we have 2 mm is order 4, so we have 4 of these equivalent general crystal faces. The square system is similar. For the square crystal system, we have point groups 4 and 4 mm. For the hexagonal system, we have 4 point groups, 4, 3m, 6, and 6 mm. For point group 3 is the top one, and for 3m, we have 2 ways of fitting the 3 mm into our system. We can have a mirror plane along the y-axis, or we can have a mirror plane perpendicular to the y-axis. This is because the angle is 120 degrees in the when we draw the unit cell, or when we use the analytical expression. So we have 2 analytical expressions for the same point group, and that again is going to be very important later. If you notice, for the equivalent planes, we have HK and I, and the reason for that is we can see above, suppose we start out with the 1, 1 plane as before, only now we operate on it by a threefold. We get the 2 bar 1 and the 1 2 bar, and they really don't give any feeling of a threefold. However, if you take the sum of h and k and you set it equal to I equal to minus the sum of h plus k, you get 1 plus 1 is 2, and minus 2 is minus 2. 1 plus 2 bar is minus 1, minus that is 1, and 2 bar 1, if you add those together, you get minus 1, and the negative of that is 1. And now if you look at these three, you can see the permutation of the 1, 1, 2 bar, the 1, 2 bar 1, 2 bar 1, 1, and that gives you the equivalent planes. And here is our hexagonal crystal system, again with the same organization. Now we'll look at the two-dimensional point group trees. There are 3 two-dimensional point groups, and they're related through subgroups and supergroups. A subgroup is a group wholly contained in a larger group. The red subgroup is wholly contained in the blue group. A supergroup is a group that wholly contains a smaller group. The blue supergroup contains the red group. And now we're going to use that information to create a tree. And here's our giraffes eating a tree. Our abstract tree is going to be a little bit different, but it's the same general idea. Now what I want you to do is I want you to print the next slide, the one with all the circles. And then you're going to fill in the point group tree along with me. It's important that you understand these relationships among the trees. These trees are so important, and so important to the theme of the book, that I have a 3-dimensional point group tree on the cover of the book. I filled in point group 2 and 6, and you'll be expected to be able to do this by yourself for the quiz on Wednesday, and perhaps on test 1. That will be required. So here we have our blank trees, and if we put in 2 and 6, which I will give you, now I want you to fill in the rest of the point groups. So point group 1 is part of every subgroup of every point group, and that has order 1. Now we move up to order 2. We have 2, and M is the other point group with order 2. And now let's combine the 2 and the M subgroups into a supergroup of 2MM. 2 also is a subgroup of 4. And then finally we can have the supergroup which contains, which 4 is a subgroup of it, and 2MM is a subgroup of it, and that is 4MM. The 2 is subsumed in the 4. Now we can go to the hexagonal system, put in the 3-fold, and now we have the 3M, and finally we combine them all and we get to the 6MM. Now we want to put in the crystal systems. The oblique is 1 and 2. We'll leave that just white. The rectangular is M and 2M. Let's color that red. These colors are arbitrary. Then we'll look at the square. Notice I've colored the square blue. The square is yellow, and we have the 4 and the 4MM for the square. And finally, we have all of the hexagonals colored green, and we're done with that first part. Now we're going to move over to the point stereographic projections. First of all, we know that we have the y-axis is horizontal, so let's put that in order 1. That horizontal axis is the same for all axes, so let's put that in for all the axes. The y-axis is the same for all of the point groups. And now we can put in the obliques, so here's the oblique axes, and finally we have the orthogonal axes, which would be M, 2MM, 4, and 4MM. And then we can move over to the hexagonal, the hexagonals, and put in the 120 and of course the 60. Now we're going to put in the identity. The identity is a red dot, and it's we'll just remind ourselves y is positive going across, x is negative going down, x is positive going down. So in this quadrant we put the identity, we choose to put it there, and it's the same, we will choose to put it the same in all of the positions. The identity is colored red because it does not change its handedness. The determinant of the identity matrix is +1. Now we can put in some of the 2-folds. There's the 2-fold for 2, and we can put in the rest of the 2-folds and the 4-folds for 4, 2MM, and 4MM. Now we can go to the hexagonals and put in the 3-folds and the 6-folds. So now we have all of the positive operations. All of those operations, the matrices represented by them, have a determinant of +1. Now we go to the mirror. When we have a mirror, we have a change of handedness. We indicate that by changing to blue. And 2MM, of course, is also going to have mirrors, and 4MM has mirrors. And now we can put them in for the rest of the hexagonals. Now we're done with the point stereographic projections. Now let's look at the symbols. Point group 1 has no symbol. Point group 2 has the point group 2 symbol, the rotation, the 2-fold rotation symbol, which is here. Now we'll put in the triangle, which is the 3-fold. The square, and both the triangle and the square have the vertices pointed upward, which is the 4-fold, and finally the 6-fold. And then we see also we have a 2-fold in 2MM, we have a 4-fold in 4MM, we have a 3-fold in 3M, and a 6-fold in 6MM. So now we're finished with those symbols, and now all we have to do is put in our mirrors, because the mirror is the only operation left. So we have the mirror for M, we have the mirror the horizontal mirrors for 2 mm and 4 mm, and for 3, and now we can put in the perpendiculars for 2 mm. We can finish the 4 mm, put in 4 mirror planes. We have 3 mirror planes for 3M, and finally the 6 mirror planes for 6 mm. And now we're done. And if you can do that successfully, you really understand how the point groups are related to one another through both the stereographic projections and the symbol stereographic projections. Here's the figure that appears in the book, which is the same one we've just derived. And finally, there's 2 more things that we can do. We can, for example, mark the cyclic groups, which are the single generator groups. They're 1, 2, 3, 4, 6, and M. They're in red. And you can see that 2 mm, 3M, 4 mm, and 6 mm all are yellow. They have two generators. And another thing we can do with the point group tree is we can ask the question, what operation is common to what point groups? In this case, we say, what point groups have the operation 2? So I start out with the 2, and now I go up the tree from there, and you can see that here is all the possibilities that have the 2-fold in them. Notice when we start with the 2, we omit the M, the 3, and the 1 because we have no way to get there in the groups. So that's all for now, folks. See you later. Bye.